Let's continue our mini course in superconducting quantum circuits. Okay, yesterday we discussed a little bit about why do we need nonlinear oscillator to create a qubit. We discussed a little bit about the energy levels of the circuit and why that is important to have this difference in the energy levels in our artificial atom. And as I told you, when we are trying to probe these two energy levels here, the first and the second one, we are not going to send only one photon here. We are going to send billions of photons, and if we are sending one photon every time, we are sending this in continuous fashion. So we are not sure when we are going to occur the transition from this state to that state. So that's one of the reasons we need to be sure that we are not exciting the other states during the experiment. Now I want to talk to you about the Josephson junction. Okay, and the interesting of this element is that this element gives us a device that can give some non-harmonic, a nonlinear effect in the system. Okay, so we can add this element in our electric circuit and create some kind of non-harmonic oscillator. And basically, the system is composed of two islands of superconductor material with a small barrier between the two parts. And basically, you can see here, you have a superconductor here, another superconductor here, and some kind of non-superconductor material here. We could use here, for example, a normal metal here, a magnetic material, isolant material here, any material that will not give us superconductivity between the two parts of our junction. And because we have a metal here, another metal here, and some kind of isolant in the middle, we will have two characteristics here. First one, when we have two small plates, each one of the sides, we have some capacitance here. So we need to add a capacitance that is related with the energy between the two sides of the junction. Okay, so we create an element that has this Cj that express this part of the behavior of this junction. Now we need to start to think about how can we describe the electrical behavior of this system. Okay, so in the next slides I will discuss this a little bit, but here I'm showing you guys an image of one junction. Okay, this junction is basically what you have is you design something. Oh, so what do? You get a slice of silicon, for example. Okay. You put on top of the silicon here polymer, okay, and this polymer you can modify the properties of the polymer in some way. Okay, have some way to modify the properties of the polymer. One of these polymers we call PMMA. Okay, you can modify the properties of this material with electrons. You can illuminate some parts of the PMMA, and you can modify the chemical characteristics of the material, and you make this material soluble in some kind of solvent. Okay, for example, water. So what we do, we came with these electrons and illuminate some regions. For example, I illuminate this region here and this one here. So I send electrons here, and I send electrons here. When we do that, we modify the properties of the electrons here, and here, here, and here. Okay? So everything here will be modified by the electrons. Also here. But if you remember from your courses of when you have an atom or something hitting some atoms, you have the electrons diffracting inside and being they will hit some other atoms inside of the material, and they scatter for some other directions. Okay? When this happens, the electrons start to move in some fashion. For example, this way here. The electron hit here, and then they can move in this direction. Okay? And the same thing here. Here, and then you can see some electrons come through all directions here. Okay? Knowing that you can do that, what do we do? Okay, let's send the electrons near and near. Here. Okay? So everything here is illuminated with electrons. Everything here is illuminated with electrons. Then we are modifying this polymer in some fashion, in some way. And then we have all of this region here. All of this region here. Modified by the electrons. Okay? Now, this part that I modified can be soluble in some liquid. For example, water is one of the liquids that make this, you can remove this material. You get this piece here, put in water, keep there for some time, and then what happens is that you can remove everything here. Then you get something. The polymer that you did illuminate to the electrons are not soluble in water, and you can keep this part here. Okay? So this, I'm looking here from the top of the image. I'm looking at this trace here, and here I'm looking for the top of the image. So I illuminate everything here with electrons, everything here with electrons. Okay? So now I have this kind of bridge here. That is that part here. Okay? So now, when you guys are arriving here, probably you passed for some kind of a bridge here. Okay? And you can see the shadow of the sun in the bridge. And you can see when the sun comes from, for example, this direction here, you can see a shadow in this part here. Okay? Oh, what the guys did. Okay, if I can create this kind of bridge here, and I know the bridge can make some kind of shadow when I illuminate it from this side, I can use that to try to create this structure here. That is a superconductor, some barrier, and a superconductor. How the guys did that? Okay, they put this sample here in a machine to do evaporation of superconductor material. Okay. One of the easiest way to do this kind of junction is to use aluminum. If you guys remember, aluminum, when it has an oxide layer on top, so when you get aluminum, you scratch. After some microseconds, you already have a layer of oxide on top. The aluminum react with the oxygen in the air and form isolate barrier on top of the aluminum. Okay, so we put this sample here in a vacuum chamber, and then we put some source that will eliminate this sample, and I'm going to evaporate aluminum on top of this device here. Okay, how will we do that? So our equipment I have a pocket here. I put aluminum here on the bottom part. I get we put past some current through a small filament. We heat this filament with a high temperature. When we heat the filament, we have thermionic emission of electrons. We have electrons coming out of the filament. Then we put magnetic and electric field and bring these electrons to heat this aluminum here. So we have a lot of electrons coming from this filament and heating here. It's important to remember that you see thermionic emission, I think in condensed matter, probably thermionic emission, the guys see that in what course? Solid state physics or structure of matter, maybe. Some of the courses you see that. And you send electrons here, and you have electrons hitting the aluminum. When you have current passing to a material, we start to heat this metal. Okay? When you start to heat the metal, you pass the metal from the solid state to the liquid phase, okay, the liquid state, and then we'll have a liquid in vacuum. You have the gas. You don't have any gas here inside. The atoms of aluminum start to fly away. Okay? So you have electrons evaporating from your sample. Okay? Then what we do, we here on top, we put our sample. Here, okay? So when the electrons arrive here far away from the source, it's basically they are coming in a straight line to your sample here, okay? So what, if you want to make a shadow here, what you have to do? You cannot change the direction of the atoms here. It's really hard to move this, everything here. So you move our sample here. You change this angle of the sample in direction of the atoms of aluminum arriving here. Okay? So what you do first? First thing, we put our sample with this angle here. When you do that, the electrons arrive here, you deposit here, here, and in this small region here, I'm not depositing aluminum. Why? Because we have this small bridge here, small part of material that's blocking the the atoms of aluminum to pass through. Okay, so in the end, you keep this for some time, and then you have aluminum deposited here and here. Okay, so we did the first part of our junction, this side here, for example. Okay, so what we do now? We need to do the barrier. We need to make some barrier here in the middle. Remember that I told you guys that when you put aluminum in the air, in the oxygen atmosphere, you start to form oxide on top of the aluminum. What we do then, we start to put some oxygen inside of the chamber. When we have oxygen here, we start to form here a small barrier of oxygen, of aluminum oxide on top of the aluminum. Okay? We can control the pressure of oxygen inside and the time we are going to keep the oxygen inside of this chamber. So we control that. We start to have a control of the thickness of this barrier here. Then I remove the oxygen. Get my sample, and then I rotate the sample and put in this angle here. So we are going to have something that's my silicon here. Some oxide here on top. Okay. Then I turn on again my filament, send electrons again to this region here, and evaporate aluminum again. Then I start to deposit aluminum again here. I do the deposition. Because of the shadow now, I'll have aluminum depositing here, 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 and here. Okay. And if you look, this small region here, what do you see? Something like that. So we will have aluminum here, aluminum here, and the barrier here in the middle. Okay. So that's what we have here. This is dark gray here is the first layer I did my deposition. Then I put this in oxygen, create the oxide layer, Then I did the second deposition. I formed this light gray here. Then I can create a superconductor, barrier, superconductor. And we can control the size of this barrier here. So we're controlling the barrier between this superconductor and that superconductor. Okay? Oh, that's the basic idea of the barrier. Now we need to understand what's the meaning.
So what's the scale of this?
100 nanometers here. Okay. You can make 1 micrometer, 2 micrometers, depend of the what's the I propose you have for the junction. If you want a junction with a high critical current or low critical current, depend of why you need that junction.
I have a comment with respect to this sputtering process, because as I know, I remember in the sputtering process, when you have these aluminum particles that is moving and going to the direction, it's like they are going in different directions. So
Not in this case.
So you have a collimation in order to
Oh,
eliminate
we don't need in this kind of here. This is something like 1 centimeter here, and this here is like 1.5 meters. So when the atoms arrive here, they are basically in a straight line. It's like the sun to us. When they arrive here near us, they are basically in a straight line.
Okay, so the way to avoid that is with the distance.
Yeah, because here is a ultra high vacuum here as well. It's not a medium vacuum. It's an ultra high vacuum here. It's 10 minus 10 torr. Okay. It's not sputtering or other techniques in this case. Okay. In sputtering, that's a problem in sputtering because you have all of these atoms are hitting other atoms in the middle. You have something more complex happening, but not in this technique. You don't have to worry about that. Okay, so you need to understand a little bit our junction now. And as Celso told me, you guys need to do some exercises so you can solve the Jefferson junction and arrive at the equations describing the behavior of the junction. But this is one of the ways that Feynman, I think it was the first one to do this way here. And basically, you think that the wave function on this side here, you have a part of this wave function in this side of the other side of the barrier. And the same thing here. You have the wave function of the right side, and a small part of the wave function of the right side is in the left side. Then, but basically, what you write the equations describing the wave function on both sides. Assume that the electrons, superconducting electrons, have this kind of behavior here. They have some density of Cooper pairs and some phase that define the wave function in one side of the the junction, and the same thing, the density of electrons the other side and the phase the other side. Then you solve here. Okay, it's not really hard. And then when you get the equations here, in the end, you can play a little bit here and arrive. The current is proportional to the sign of the difference of phase in both sides. So the current of the passing through the barrier is proportional to the difference of phase in both sides. And the voltage between both sides is proportional to the rate of change of the phase. Okay? Oh, here is a more, this is the usual way you see many articles here. Current goes with a constant that depends on the fabrication, on the sign, and the voltage goes with the rate of change of the phase. Okay? Then this is the two equations that describe the Jefferson junction. So you can see why this is not a linear device. Because the current goes with the sign. So when we start to increase the difference of phase, some moment they start to decrease the current again. Okay? And if you get the voltage here and compare this with the inductor, okay, play a little bit with both equations, you can see that you can think that this junction here has a behavior similar with an inductor, but a nonlinear inductor that goes with the inverse of the cosine of the phase. Okay? So have this phi naught, 2 pi I naught here. That's basically what we call here the inductance of the junction, and a factor that goes with 1 over the cosine of difference of phase of both sides. So this is an inductor that the inductance of this junction changes again with difference of phase of both sides in a sinusoidal characteristic. Okay. Well, now that we have these equations, we can think, how can we see the behavior that this junction will induce in our circuit? Okay. So first thing, we need to some kind of element to describe the junction in an electrical circuit, a lumped element circuit. One way to do that is that we use this. We have Cj, that's the capacitance between these two leads here of the junction. That's the capacitor we have here. And one behavior that's because of the tunneling of the superelectrons in your device. Okay? And now let's play a little bit here with one small circuit with some of the elements we need here. You have like the two islands here, okay? The barrier in the middle. We're going to put a capacitor here to change the number of electrons in this part of your circuit. We have some source to give energy and to move the electrons in your circuit. Okay? Then we can start to write the equations describing the behavior of the circuit. So first thing we're going to do is, what's the capacitive energy you have in this kind of circuit here? Okay, you have some energy because the capacitive energy because of this Cg here, okay? And some of the energy because of this Cj here, okay? So the total capacitive energy will depend of the charge Qj and Qg here, and square over 2 divided by Cj plus Cj here. And when you put here the charge you have in this island here, because of this capacitor and that capacitor here, you arrive something like that here. Okay? So 2e squared n minus ng squared over 2 Cj. And what you see here is that the Ng here is the total number of electrons you have on your system that you can control, change the voltage here. You increase the voltage here, you add one more Cooper pair from one side to the other. Okay? And this is the energy, capacitive energy of Josephson junction. That's the first part we need to describe the behavior of a Josephson junction. The other thing you need is the energy because of the Josephson energy of your device. And basically what we're going to do the integration of Vi dt. You have V and I from the Josephson equations. We do some math and arrive the Josephson energy proportional to Ej plus a cosine of the difference of phase of the wave function of both sides. Now we have here the energy of this junction because of the capacitive energy and because of the Josephson energy. And this is the interesting part here. This part, the Josephson energy gives us this cosine factor here. That's the nonlinear part of the equation that's interesting to do the calculation here. Okay? So we now can start to think about what's the meaning of these two terms, the Josephson equation. Okay, this first part here, that goes with 4EC, that's a constant basically, n minus ng squared, okay? We can make the graphic of this. This is a parabola. You can see here, for example, in the red one here. This is a parabolic behavior here of the energy as a function of this n here. And here I have the ng. I can start choose n1. Ng is equals to 1. You change n here, you have this behavior here. When ng is equals to 2, have this behavior here. And ng equals to 3, have this behavior here. Ng equals to 0, have this behavior here. Okay? Now we can add the Josephson term here. The Josephson term gives us the term that you open the gap here. Okay? You interact the electrons from one state, from one ng to the other ng. When you have that, you open a small gap here that's proportional to Ej. Okay? Then you have the characteristic image you see in many books that describe the behavior of a Josephson junction, a Cooper pair box, basically. And you see here that when we are in ng equals to half, you open this small gap, and this blue part here has a characteristics of ng equals to 0, and this red part here has a characteristic to ng equals to 1. Now here you can adjust ng on your device. Here, we'd find Vg here. Put this junction in this region here, and you can use this small gap here as your qubit. That's the first way the guys did that. Nakamura used this kind of device to make this kind of Cooper pair box. It was one of the first qubits using superconducting devices. Okay. Now you can think that you can also have a superposition of the two states of one extra electron on one side of your ion, or one extra electron on the other side of the junction. You can use this, make a superposition of this macroscopic wave function in both sides of your system. Okay. And you have start to have an idea how can you create this superposition state in this kind of device.
One question. Is it possible to work as a qubit also?
Yep. Most part of the transmons we use today are qubits. That's normally we don't worry a lot about the third state, but it's there. For some experiments, it's really useful. For other experiments, not so much. Okay. If we play a little bit with the CG here and EJ, we can make this flat as well. It'd be much more easy to understand in this case. Okay. So what we have now, we have that Josephson junction that has a capacitor and this inductor. And the inductor has that, is proportional to the difference cosine of the difference of phase of the wave function in both sides of the device. So what's the meaning of that? That when we start to write the Hamiltonian describing the behavior of LC circuit and the behavior of this Josephson junction, the energy level between the first and the second energy level is different from the energy levels between E equals to 0 and E equals to 1. So the energy between these two, 0, 1 here is, for example, 5 gigahertz, and between E1 and E2 is 4.7 gigahertz here. So we have a difference of energy between the two different levels. That's different from a harmonic oscillator that has all the energy levels identical. So this gives us the nonlinear element that we can use to send photons in this frequency here and only induce transitions between these two levels and not induce transitions here. Okay. Okay. Now that we have a better idea of the main elements we have in the circuit, let's start to try to write a Hamiltonian describing the behavior of a circuit with the main elements we described before. Okay. Here we have the harmonic oscillator is LC circuit. And here we have our Josephson junction with the capacitive energy of the junction, plus extra capacitor I put here to adjust the energy levels of my circuit. Okay? Then I can think of what's the phase I have in this part here of my device that I will call phi r, and what's the phase of the superconducting wave function in this part here that I will call phi j. Okay? So remember that the voltage you have between any superconductor, the voltage when you have is proportional to the difference of phase, the rate of difference of phase. So the rate of change of the phase is proportional to the voltage. Okay? So you get what's the energy you have for a capacitor, the C in here. It will be proportional to the CV square over 2. But V square is phi r dot square. Okay? So you have the first part of your term describing this capacitor C in here. Then you do the same thing for CR. Then for CG. But in CG, you have the phase, the voltage in this island here in blue, and the voltage in the island in red. So you have to put the difference between the two voltages. Then you have to add the voltage because of this capacitor here. Then you have the potential energy because of the inductor here, the Josephson junction, and because of the source that's putting energy in your system. Okay? Then you write the Hamiltonian of the system, and after some math, you arrive in this equation here. Guys, this case here is a semi-classical, okay? Describing the behavior, the Hamiltonian of this circuit here. Okay? That's basically the idea when you have to write the Hamiltonian describing this kind of circuit here, you do something like that. Now is the fun part that you have to relate that equation with the equation describing the interaction between an atom and a cavity. Okay. If you guys want, you can go look how to try to arrive here. The first part is easy, it's 1 page, 1.5 pages. But there are some parts here that you have to do that will take you like 3 or 4 pages because it's a nightmare of a lot of charges everywhere, capacitors everywhere, and you have all kinds of terms. It's not hard, but kind of some work. Okay. Oh, you can rewrite that equation in this form here. Okay, you have your harmonic oscillator, have a part because of your qubit here, and you have a term that's interacting both sides, the electromagnetic field and the charge on your qubit. And the term that describes the spin square, root mean square voltage you have here on the island. Okay. So this is a way to relate the electrical circuit that have here with a Hamiltonian that will describe the behavior of this circuit here. And you see, this equation here is similar with the equation describing the interaction between atom inside of a cavity. So this we start to give you the way that you can use to relate what you know about cavity QED with the circuit QED, which you can understand what's happening in one circuit and the other circuit. Okay.
So I have just a question. In this analogy, like phi and phi dot are like my position and momentum, right? So I would write the annihilation operator as a function of phi and phi dot.
Yep.
Okay.
Oh, this equation has is similar with this one here, James Cunning type of Hamiltonian. Okay. So we can analyze that equation and arrive the ground state and the excited state for this kind of Hamiltonian here. And now you have the usual way you can understand the energy levels of an electric circuit and compare these energy levels with the what you have in cavity QED, and you can start to make quantum computation. Okay. Okay. So something that is interesting in this kind of superconducting circuit is that you can work on, you can adjust the interaction between the electromagnetic field inside of the cavity and the dipole describing your transmon in a regime that we call, that the interaction is really strong, have a really strong interaction between both systems. Because okay, let me show you here. Remember, I have that planar waveguide here. Then you have electrical field inside of the cavity here. Okay. So you create an electrical field here, but these dimensions here are around 3 to 4 micrometers. You can create a really strong electromagnetic field here. The electric field inside of this region is really strong. Then your qubit is really big. Around 1 to 2 micrometers. So you have a really large dipole appearing there. So you can have a really strong interaction between the electrical field and the dipole described in the junction. Then you do some kind of play a little bit with that Hamiltonian and can rewrite in this way here. And this is really interesting because you can see here, A dag A represents the number of photons inside of your cavity. Okay, you are here describing this electrical field here inside. And you see that this term here is multiplying these two values here. Chi, that will be basically G squared over delta, that this is here is the difference of frequency between the qubit and the cavity, okay? Times sigma Z here. That's the state of your qubit, okay? So the frequency of resonance of the cavity will be modified by this term here. So every time you put the qubit, for example, in the excited state, what happened with this frequency, the total frequency here, omega C minus chi, you'll be subtracting from this omega C here, this term here, chi. So you are shifting the frequency of the cavity. So when you are looking at the cavity here, frequency, transmission here, you have here is the transmission of a cavity as a function of the frequency. When we excite the qubit, for example, here, the cavity shifts frequency. Okay? When that happens, what do you see on this image here? You see this shift of frequency. So what we do in the lab to be sure that this is changing? We go and start to look, for example, one frequency here. We start to look at this frequency here in our system. We are not looking at all the frequencies. We choose only one frequency. So I come here. I will start to look at this frequency here and see the transmission of this value here. For example, here, 0.8. Here I see 0.8. Okay, I start to see this frequency here. Then I start to excite the qubit. Okay, I try to send a signal to excite the qubit to see if I can induce the transition I have in the qubit. When we saw there, here, the transition here was around 5 gigahertz. So here I put frequency. I'm going to probe the qubit. I start here, for example, in 4.9. I'm going to 5.1. And 5 is here. Okay? I start to send photons to the qubit, and I'm looking this point here. I'm going to look at that. When the frequency I'm sending to see the qubit hits 5 gigahertz, that's the energy of the qubit, what happened? The cavity shifts here. Then I'm going to see the transmission through the cavity changing to this value here. For example, 0.5. 0.5 here. When I start to arrive here, I start to see. Okay. That's the basic idea of what the measurement. So when we have this equation, we can start to see this kind of behavior inside of the our device. So we see something like that happening. But there is a detail. Depending on the state I have here of this mode. What's the state I have inside of this electrical mode here? I have 1 photon, 2 photons, 3 photons, 4, 5. How many photons I have there? Does it change the way I will see this here? So, if you guys remember, I think I showed that in the beginning. Let me open here. Here. Hey, remember this graph I showed you guys in the beginning of the talk yesterday? This is what we are saying. We are probing the cavity in a specific frequency, and then we are changing the frequency, we are exciting the qubit. Okay? Then we see these different peaks here. And these peaks are related with the qubit interacting which one of the photons I have inside of the state of the cavity here. When I have this cavity here, each one of the photons that describe, for example, here in a coherent state inside of the cavity, you excite the qubit again. And then you will have a change in the frequency of the cavity. Okay. Okay. So that's the basic idea we use to use a cavity to measure the qubit. So when the cavity shifts frequency, we know the qubit is in one excited state or the ground state. And that's what we do in the lab. We probe we do all the operations in the qubit during some time. In the end, we want to see what's the state of the qubit. If the qubit is in the excited state, of the qubit is in the ground state. And we send, in the end of the process, we send a pulse that you probe the cavity and see if the cavity is in the excited state of the ground state. If I see the cavity with this transmission here, okay, the ground state. If I see with this transmission here, is in the ground, is excited state. Right? Okay. In the experiment, it's a little more complicated because we don't have, normally we don't have only one cavity. We have many cavities there. Each one for each qubit has a specific cavity to do the measurement. So we need a specific way to send a signal that will probe all the cavities at the same time, recover the signal of all the cavities. Then we need to do some calculations and some operations on top of the signal to recover the information of each one of the cavities we have inside of our chip.
Short question. You have the cavity to measure the
qubit
state. Okay.
Yep.
But you also need another cavity to manipulate the qubit state, right?
You can do directly.
You can use the same?
Yep, that's a good question. I was not thinking to describe that, but okay, there are some ways to do that. Oh, you have something like that here, okay? No, you have a source here. You send a signal passing through this cable here. And the cable goes out here, you put some amplifier, and send this to your computer. Okay? Then you need some kind of cavity here. You have another cavity here, another cavity here. Okay? Each one of these cavities will measure 1 qubit. So, and I need to connect this to a qubit here, a qubit here, a qubit here. Okay? One way to send signals to the qubit is to put a second source here. That will send the signal to this qubit. You put some signal here that will excite this qubit, increase the power a lot like crazy, send the signal to this line. Some of the power will couple from this line to this line here. You pass through this line, and here, you couple to your qubit. So by brute force, you increase the power a lot, and there's some signal, you go to the lines and arrive here. Okay? That's one way to do it.
But it also goes to the other qubit.
To everyone. Goes to the everyone. But if the frequency is different, there's no problem. If the frequency is similar, you start to have problems.
Yeah.
Okay.
But if you have 3 qubits, you can choose frequencies in such a way that they are really different.
Yeah, you can. Yeah.
But if you have 10, it's more different. If you have a million.
Oh yeah, but that's one way to do it. You have another way. Then what you can do is you can have a source here. That will be coupled to this qubit here. Okay? You send this signal directly to this qubit here. And you can start to think about, okay, then next qubit here, I can use another source. And send this to this qubit here. You see, you have the same problem because you need many of those devices here. And that's one of the things the guys are doing. The last IBM talk, they showed one of the equipments to do this kind of measurement. It's a rack with all kinds of sources here, electronics to send signals to each one of the qubits to do the operations. It's a monster, and that is a challenge for the engineers to do that. It's really complex. It's really hard to send the signals to everyone here. But that's the way they are doing. One way is to have a chip, a semiconductor chip that will be around 4K, that you create the signals for each one of those systems. Or you have a chip that is together with this device that you send the signals to each one of the qubits. But that's an engineer problem. There's a lot of physics inside, but that's not the idea of what I had here for this kind of talk.
Engineering problem.
Yeah. There are many good physicists working on that, because that's a real problem to make the computer. And that's something we are trying to do in the lab, like have a semiconductor chip together to send signals for the qubits. So I don't have to send the information for my semiconductor chip that to create the pulses for but only for a small scale, like 3 qubits, 4 qubits, 5, no more than that. Okay. So after that, that's a company problem. That's IBM problem, not my problem. Okay. Okay. Now you send the signals to each one of the qubits. To measure the cavities, it's easier because you have each one of the frequencies here, 5.1, 5.2, 5.3, for example. Okay. You can do the following. You have a signal with 5. Let's put here 6 to not conflict with 5 here. So 6, 6, 6. Okay? So we have a 6 gigahertz signal. You mix this signal with another signal that will be 0.1 gigahertz, 0.2 gigahertz, 0.3 gigahertz. You put this signal for each one of those. You mix with this 6 gigahertz here. You get all of that signal here. You send here inside. So you have a 6.1, 0.2, 0.3, and 5.9, 5.8, 5.7 as well. But you have some ways to play to have more one side than the other of your system. That's an engineer problem as well. So you have this signal here. You send the signal together with that one here. You mix in some specific way. You send it here. Then each one of the signals, you probe each one of the cavities. Then you probe each one of the cavities. Then you see that change here happening for each one of the signals. Then you recover the signal here in a computer and a lot of electronics here in the middle. And then you compare with your original signal. Then you can have information about qubit 1, qubit 2, qubit 3. If this is 0, here is 1, here is 0, for example. You have information of each one of those. And you repeat that same measurement 1 million times, then change some parameter, repeat 1 million of times, change again, and then you start to construct get the information you need to really see if what you are doing is what you want. Okay. Oh. Okay. I'm not talking about the details here. There's a lot of details here. I'm not going to talk about that today, but that's the basic idea of what's happening. Okay. And that's only 3 qubits. Then you have interaction between the qubits here. You can, between these 2 here, you add a second source here that you change this one here. Then you can start to couple these 2 here. And then you can do the same thing here. And then you start to have interaction between the 2 different qubits that you can control when you are turning on and turn off that. Or you can do the other way, that you can have this one here, a cavity here, coupling both. So the coupling is always on. Oh, there is different ways depending on what you want to do here. And you need to start to think about what happened when you have 2 qubits together, what's the noise you are adding here, what's the interaction you have because of that. And then you have interaction between this and that as well, and this and this and that. You start to have like big problems that you have to solve. inside of your chip. Okay. Okay, so this is a little bit more complex because they have a lot of electronics, and you need to know the Jackson really, really well, because there is a lot of interaction between everyone here. And that's not the idea of this mini course. Okay. So now let's see here. Let's come back to the photolithography. That's the way we make the sample. How we are going to do to create this sample. First thing we do, we did everything I told you before. We're going to start to planning what we want to do during the experiment. We're talking with theorists to have an idea of what we're going to do. We do some models, we do some simulations. Then we start to draw some circuits that will describe our Hamiltonian here. Okay. In this example here, I have here a capacitor, that's my mirror here. I have another mirror in this small region here. And this small curve here is my cavity. Okay? And then I put a qubit here, another qubit here. Okay? And what we are trying to do here is I want to probe this qubit here, then probe this qubit here, and know the characteristics of the qubit I create in the beginning. All that processing of oxidation, deposition, all of that, I want to create that atom, artificial atom, one here, another here. Then I do some calibration. I know where this qubit is and where this qubit is, and I know the frequency of the cavity. I know the energies, the coupling of everyone here. And because of this qubit and that qubit are in the same cavity, I can interact both through the cavity. I can have one qubit interacting with the cavity and the cavity interacting with the other qubit, and I can try to interact both qubits together. And this is the design of the first 2 qubits we building our lab and measure the last couple of months. So this is the design of the chip here. The qubit, the first 2 qubits we did or in a sample exactly like that. Here another sample that I have 4 qubits, and I have a line here that I can probe each one of the cavities and have the qubit, each one of the qubits not interacting with any one of them. So have this qubit here interacting with this qubit, this one interacting with that one here, and the cavities here in the middle to probe the qubits. Okay? And here is an example how I do the first step. That's when I want to create this kind of circuit here, I need to start with the superconducting material. So how we do that? How can we, with the idea of the circuit I have, I can draw something and create the electrical circuit. We do something similar what we did before with the Johnson junction. Okay, we get silicon wafer and put aluminum or niobium on top of that that wafer of silicon. Okay, when I have the silicon covered with this superconducting metal here, I put some kind of resist, again, a polymer that I can modify with some light or electrons or some other way. I modify some part of the polymer and remove this part of the polymer. Then I came and remove the niobium or the aluminum in that region. Then I remove the resist, the polymer, and I'm left only with the regions I want to keep the metal. When I do that, I can have this dark red here. I will remove the metal. The light red here, I will keep the metal. And I can do the other way around as well. I can have put first the polymer, then do the position of the metal, and then when I remove the polymer here, the metal that's on top of the polymer will go away with the polymer and the solution I'm using to remove. Normally we use it this way here because we have some technical problems here. There's some problems that we need to address here and we don't have to address here. But there are other problems here, so it depends on what machine we are using, what we want. Again, this is not the idea of the mini course. Okay, so then we are going to have a sample like that here. Okay, see the light gray here, that's metal, and the dark gray here, that's silicon. And here you have a sample with 2 qubits, and here a sample with 4 qubits. Okay, that's image that we took using electrons, so using SEM to do this image here. And here we have optical image showing you the transmont here. So this is the 2 pads that are creating the capacitor I have in my junction. So remember I told you guys that have the junction, EJ and CJ here. So this symbol here, that's a square with a cross in the middle, is a capacitor and the junction. And then I add a capacitor here. Okay, when I do that, I change the energy as a function of energy of my device from something like that to something like this, okay? So you can see here, this is a flux line to change the flux passing through my qubit. So I can change the energy of the qubit. Here I have the cavity coupled to my qubit here. Here we have the control line that can send the pulses to excite or manipulate the qubit here.
This case is different for the example that you showed there where you manipulate the qubit just with the same line, right?
Yeah, this is a little bit different. That's other design here. Okay. So here, this is the capacitor. Here the line, we are coupling this line here with the qubit using a capacitor as well. Okay. Then we need to calculate all the capacitors here between everyone, and then we can have an idea of what's the coupling between each one of the elements in my system. Then, after we have a sample with the pads for the qubit, we need to go there and make the qubit, the junction. That's an image of the equipment that do that. Here on top, we have the column that will create the electrons that will make my draw on the sample. Then I can, machine, bring the sample to this position here. That's aligned to these crosses here. Then go and draw this kind of design here in this region here. The machine goes and starts to send electrons in this region, specific region here, and that specific region there. Okay? Then I have my bridge here, and then I can go to my other machine and do the deposition of aluminum. Here's an image of the junction, and here is an image of here's the bridge. You can see here, I don't know if that's possible to see from the top there, but there is a small dark region here that's defined the region that was the shadow of this junction here. That's that bridge here. Okay. Here's a side vision. You can see here the metal deposited here. The bottom part here is where the polymer is, and the top here you have aluminum on the top. Then I'm going to another place, and then I remove the polymer, and I only keep this part here. That is the junction. Okay. Okay. And here is the image showing the what the electrons do inside of my system. When I illuminate the sample with electrons here and here, electrons scatter through the polymer. Then when they do that, they become soluble in water or any other solvent. I remove the polymer from this region. I do the first layer of deposition, for example, here and here. Do oxidation for all the aluminum, and do the second deposition of aluminum top. Then I remove my sample from the chamber, and I have my junction here. Superconductor, the light blue here, the oxide, and the dark blue, the superconductor again. Okay. So this is all the steps we took until now. First, we design our sample, the cavity, the qubit. These are for some experimental modification of the sample. It's not important right now. We create our qubit inside of our sample. And we can start to play now with the device. Okay? So how can we do that? We need to put our sample inside of a dilution refrigerator that will give us the environment necessary to see the quantum effects we are looking for. Remember, the energies of the electrical elements here are around 5 gigahertz. So we need an environment where I can see this energy on top of my noise. So 1 gigahertz is around 50 milli-K. Okay? So if I'm in a temperature of 50 milli-K, anything that has 1 gigahertz is not possible to see. It's really hard to see. Because 50 milli-K, you give a noise that's proportional to 1 gigahertz. So what we do, we put the sample in a very low temperature here, 10 milli-K here. Then we connect my sample with some lines to bring the signals from room temperature to my device. Then, because the noise of electrical noise of room temperature is really large, I need to remove this noise from my signal. So I create a really large signal. Then I have the signal plus the noise there. Then I start to attenuate both parts of the signal plus the noise. And I reduce each one of these stages to thermalize the signal with that temperature and to reduce the signal that I create in the beginning really large to send this signal to my sample. So I can probe now, for example, the cavity, and I can just send the signal through the same cable here and to excite the qubit. Then after the signal arrived here at really low temperature, the signal is really, really small. If I get the signal and send directly to room temperature, the signal will be much smaller than the room temperature noise. So what we do, we pass through some circuits to remove noise from my amplifier. Then I send my signal to a single electron transistor that is really low noise, that will increase my signal and increase my noise to values that I will be able to see at room temperature. So I have a lot of amplifiers here, some way to treat the signal, to send the signal back to room temperature where I can distinguish the signal from the noise I have on the background. So now we have all the elements here to start to do our experiments. Okay? And the first experiment we do is to see the cavity. First thing I need to see if I can see my cavity. If I cannot see my cavity, I cannot do anything. No, we connect equipment that we call here VNA. That's basically, I'm measuring the transmission and reflectance of my signal arriving to my sample. Okay? So I send the signal here. So the signal comes from all the cables here. arrive to my cavity, come out of my cavity, exemplified, then come back here to my analyzer, okay? What this equipment do, they compare the signal that I send with the signal I receive back, and they can get information about amplitude and the phase change during this, during the time the signal passed through my sample, okay? Then I have, for example, something like that. Have a peak with some specific frequency here, for example, 5.89 gigahertz. And from this peak here, I start to get some information about my cavity. For example, the kappa of my cavity, how much leak I have in my cavity. And that's that kappa I show you guys in the beginning of the talk yesterday. Okay? Have a cavity, and the cavity has some leak, have information of the leak here. And then from the phase shift, I also have information about the leak I have in the cavity. Okay. Now I want to start to talk with you about how we do the measurements to probe the qubit and to see if my qubit's alive. Okay, the first thing we do when we have a sample with a qubit is to see, okay, after all that process I did in my sample, the qubit is still there. I have a Jefferson junction. I have a qubit that is alive inside of my device. And that's the kind of measurement we are going to do. It's similar to what I have here, but there are some differences that are related with the Hamiltonian of the system that we are going to discuss a little bit tomorrow, because today is already 10:45, and I need a coffee. I think you guys need a coffee as well. And we have another talk later today, okay? And everyone want to see the game, so I believe everyone want to go home or go to a bar or some place to have some beers before the game. Okay, so I'm going to finish here today, and we start from this point tomorrow. Okay, guys? Thanks. Oh, questions?
You need a lot of electronics, right? So
A lot of electronics.
I guess more than physics
Oh,
for this part of the.
you need to understand a lot of physics. A lot of physics. Not only quantum mechanics. You need electromagnetism, thermodynamics, solid state. You need to remember everything you learned during your undergrad course. And some extra material from the engineers.
Do you have engineers in your group?
Only from the side of computer engineers.
Okay.
They go there, but they want to only learn about quantum mechanics and quantum computation. They don't want to work a lot on that. Not really true. I have an undergrad student from that work with. He's working with to try to create, simulate a quantum computer in a classical computer. Basically, make a 3 or 4 qubits and try to apply Shor and Groove algorithms there. And I'm putting this student to now to manipulate the data that's come out of the measurement, and he's going to parallelize that to GPU. Because this is something like I have 1 giga sample of data come out of the measurement all day. So I need to treat all of that data to have the information I want from my my qubit. So I need to do parallelization of all of that data. So the guy is on C and assembly writing the codes to create this kind of processing.
Okay. And I have a question now related to physics. So the size of your device, of course, if it's bigger, you have more electrons inside. And so the current, the superconducting current will be larger, right?
Depends of the voltage you have there in the end. Depends of the voltage you have. But where in the system?
I mean, you said that the size of the superconducting island there
Yep.
is something around microns, right?
Yeah, the qubits, the transmon qubit we are using is basically that.
So if you have a
Here
bigger-
is 100 micrometers.
Okay, but the piece of material, the superconducting material, how big is?
This
Yes,
is 100 by maybe 400.
400. If this becomes bigger,
The,
how the quantum effects?
that's
does
not
not-
a problem in the end, because what we need here is the capacitance between these two sides here. What's the capacitance I have here? That doesn't matter really a lot to us, because what matters is what's the critical current here? What's the critical current here? That will give us the energy
It
of the
depends
junction.
depends only on the gap, right?
Yeah, we build this to have a specific energy, a capacitive energy that we, together with the Joseph's energy, you give us qubit energy around 4 to 8 gigahertz. That's what we want. We want to build this capacitor and the junction here in values that will give us something around this region here. So if I want 5 gigahertz, I need to modify the capacitor and the junction to create 5 gigahertz. If I want 6 gigahertz, I modify both to do that. If I want 10, I need to modify again.
Okay.
So, and the critical current here and the capacitance are the terms I need to adjust to do that.
In order to see the quantum effects.
Yeah.
Okay.
Because the power I have there is really, really small. It's nanovolts or less than that. It's really small voltage, and the current are really small. If I increase a lot, I start to have no linear effects there and start to have to worry about the terms that I throw away during my calculations.
Okay. Okay, thanks.
So, thank you, Professor. So I have the feeling like you're trying to do everything on site with your equipment.
Yep.
Is there anything you're outsourcing and you're getting from elsewhere?
Not now. I'm doing everything in the lab because I need to do some training of the students. Because I'm the only one that knows how to do that now in Brazil. So I need students, I need to get students, okay, we are going to learn from the beginning, everything until the end. So he's going to learn all the details I have here, how everything's working here, how to make the samples, how to build the device, how to create the programs, how to control machines, how to simulate everything. The student needs to know everything.
Okay, so this leads to a further question. Since you're probably the only person doing this in Brazil,
I think so. I don't know any other person that's doing that. If you guys know, please let me know. I need someone to talk.
It was good to start there in Rio de Janeiro, as you know.
Yeah, but I'm working with him, so we are basically the same group. I'm teaching the guys there. So
Yes, so you don't have any postdocs coming from elsewhere also
if I
and
pass
working
me,
with you?
you give him the money, I can hire anyone. That's a problem with FAPESP that, because I just started here in Brazil. So FAPESP told me, oh, you are too young, you cannot have postdocs yet.
Because there's no PhD.
No, so I cannot have.
This is an amazing rule we have in FAPESP.
Yeah. But in the rest of the world, the first one you hire when you have a lab is a postdoc, because the postdoc will put the lab to work. Yeah. Then you hire the rest of the people. Yes. Here is the other way around. Yeah. First you hire undergrads, masters, and the PhD students. Then you start, okay, now you can have a postdoc. Yeah. That doesn't make any... Other way around. The rest of the world is wrong. Only Brazil is right.
Okay, cool. Just I wanted to get a feeling of everything around.
Today is really hard in the lab for a postdoc because we are building everything, and everything goes here in Brazil really slow.
Yeah.
And when we have a problem, it's like 6 months to solve. Outside, in the rest of the world, I have a problem. And go to internet, I need this, enter, send me overnight. Next day in the morning, you arrive in the lab, everything's on front of your door, you get everything put in place and then start to work again. But we can do that here. You just need a lot of work and patience and some time.
Oh, yeah, so I have another question.
So also I would like to have an idea of, because when you're building the chip, it has a lifetime, right? You can use it for some time and then you have to change it or
yeah, when I said, okay, let's start to make a sample, I need to get the sample, and 200 hours after, I need to have the sample inside of the fridge. If the sample isn't on the air more than 200 hours, I have to throw away the sample.
Okay. Okay.
Okay, thanks. Are there more questions?
For me, very nice to listen you that you are building your lab in order to do this, because I came from Argentina, in Bariloche, and there is in the Instituto Balseiro. They are already creating a lab for this. They just buy the cryostat from Blue Force, but the cryostat is in the airport right now. It's not in the lab. So they are very in the beginning of this. And for me, it's very interesting to know what are your current projects or your main interest in your lab in this moment? Or in what project are you working in this?
We have many different works in the lab. We have a line that will be classical quantum transition. So we are building a microscopic device that I will couple with these superconducting devices. I want to see if something happens when I go from a microscopic sample to a macroscopic sample, and if something happens there. If I have something different. Sorry?
This was what I was trying to ask you, because when you look bigger systems.
Yeah, in this case here, there's no difference because the superconductor, I have 1 ton of superconductor. Doesn't anything change there. But I'm going to add some element here that has some property that can be related with a microscopic property. For example, I want to add a mechanical resonator here. And this mechanical resonator, when I start to increase the size, maybe some moment I maybe can see something different than what I expect from classical mechanics and from quantum mechanics. Okay, that's one of the lines. The other one, we are trying to work with quantum clocks. We are trying to put a quantum qubit and make the qubit work as a clock. Put in the superposition, they are rotating there. I put the qubit there, and then I pass a wave through the qubit as a matter wave, a gravity passing through the qubit, and then I want to see some precession or some acceleration of the clock. I use the qubit as a clock, a quantum clock, to see what happened. But the theory is, we had a student doing that in his master, so he did all the equations, everything. Now we are writing the paper, but I don't put the paper outside before I do the experiments, because the moment I put the paper, someone will try to do it. And the other one, we are working with the hyperbolic lattices. We have a lot of these microwave cavities in a configuration that in the end we can simulate it in this kind of circuit some kind of crystal that does not exist in 3 dimensions. They only exist in 4 or 5 dimensions and have different structures that are not expected in Cartesian universe. Okay. Other work, we use thermodynamics, quantum thermodynamics. We are trying to build some single electron transistors that we are going to try to make some kind of cycle and see what happens with the energy and heat inside of that system. So you bring lines from different stages that you introduce heat one direction and the other, and have a cold and a hot region in my sample and try to see if I can play a little bit with the heat inside of the circuit. But that part, I'm not really sure how I'm going to do that. I have some ideas, but I need to get some guy working with theory. Okay, sit here and let's do the math together to see if it makes sense of what I'm thinking. Okay. And there are some guys arriving every day in the lab asking to do stuff, but I need samples. Like Ivan told you guys yesterday, he can put some chloroform there on the machine, turn on and start to play there. I need samples that I can go put on my refrigerator and they start to play. So I can start to do some real physics. Okay.
No questions? Well, I guess we have to finish right now.
Yep.
And now we have the coffee break, so half an hour, it's enough. So 11:30 we'll be back for the last talk of the morning, Professor who is here. So let's go to the coffee break.